Hi guys, Galen here, working through a problem from WebWork homework number 10, problem number 12. The problem given to us was a spring with a spring constant K of 20 pounds per foot is loaded with a 10-pound weight and allowed to reach equilibrium. It is then displaced 1 foot downward and released. If the weight experiences a retarding force in pounds equal to 4 times the velocity at every point, find the equation of motion. So first step, we can set up our initial conditions for the problem. Finding our k, our m, and our beta, so we can then set up our linear differential equation. So our k is given to us right in the beginning of the problem, a k of 20 pounds per foot. Our m is equal to force over acceleration due to gravity, so in this case our force of 10 pounds over 32 feet per second gives us an m of 5/16. And finally our beta is equal to 4 times the velocity, so our beta is equal to 4. We can also set up our initial conditions for the problem. Once we solve for our coefficients, we know that our y of 0 is going to be equal to 1 because it is displaced 1 foot downward and released. And then we also know our y prime of 0 is equal to 0 because it did not have an initial velocity when it was released. Next, setting up our differential equation, we have the generic form of the differential equation given right here. My double prime plus beta y prime plus ky is equal to 0. And we can just substitute our values in here into the equation. So we have 5/16 y double prime plus 4y prime plus 20y is equal to 0. We can then divide everything by 5/16 so we can get a 1 as our coefficient in front of our y double prime. Doing that, we simplify the equation to be y double prime plus 64/5 y prime plus 64y is equal to 0. The easiest way for me to solve this equation is using the quadratic formula. So using the quadratic formula, we know our a is going to be equal to 1, our b is equal to 64/5, and our c is equal to 64. Setting up the quadratic formula, negative b plus or minus the square root of 8b squared minus 4ac all over 2a. We get an m1 value of negative 32 over 5 plus 24 over 5i, and an m2 of negative 32 over 5 minus 24 over 5i. We can then substitute these values into and create the complementary equation. And so we have y sub c is equal to negative 32/5 t times c1 cosine of 24/5 t plus c2 sine of 24 over 5t. And that is our complementary equation. Our next step is to solve this equation using our initial conditions that we set up earlier. So we solve for our using y of 0 is equal to 1 because it was released 1 foot below the equilibrium point. So we set our equation, our y sub c equation up here equal to 1. So we have 1 is equal to e to the negative 32/5 times 0 times c1 cosine of 24/5 times 0 plus c2 sine of 24/5 times 0. And so we have 1 is equal to e to the 0 times c1 cosine 0 plus c2 sine 0. E to the 0 is just 1. Cosine 0 is 1. So we have 1 times c1 plus c2 times sine 0 is 0. So we have c1 is equal to 1. Our next step is taking the derivative of our y sub c equation so we can apply our next initial condition where y prime of 0 is equal to 0. So to take the derivative of this equation, we'll use the product rule, u prime times v plus u times v prime. We'll first take the derivative of our e to the negative 32/5 t, and so we'll have y prime of t is equal to negative 32/5 e to the negative 32/5 t times this section equation right here because we didn't take the derivative of it, we're just leaving that as it is. And then we'll add e to the negative 32 fifths t and take the derivative of this equation or this section of the problem here, and we'll have negative 24 fifths c1 sine of 24 fifths t plus 24 fifths c2 cosine of 24 fifths t. We'll then set the equation equal to 0 and set all of the t's equal to 0 in this equation here, and solve. Doing this, we find 0 is equal to negative 32 fifths times 1, because our e to the negative 30, e to 0 is 1, times c1 times cosine of 24 fifths times 0, which gives us 1, and then this a sine of 0 is just 0, so c2 times 0, plus 1 times c1 times 0, because the sine of 0 is 0, plus 24 over 5, c2 of 1, because the cosine of 0 is just 1. Simplifying this equation down further, we'll have 32 fifths c1 is equal to 24 fifths c2, and then solving for c2 and substituting our c1 value of 1 into the equation, we will solve our c2 to be 4/3. We can then substitute these values of c into our original y sub c equation and find our general solution, and that is y of t is equal to e to the negative 32 fifths t cosine of 24 fifths t plus 4/3 sine of 24 fifths t. And that is our final equation of motion for this differential equation of a spring. Hope that helps. Thank you.